Two theories of dimension. You don't need it.
That's what he told me.
Oh, okay.
Yeah, I need it.
Yes. Well, yeah, whatever he says goes.
First of all, I'd like to thank the organizers for organizing this wonderful conference and also for inviting me here to give a talk. I'm going to talk about I'm going to talk about the work recently finished with Sergio Ceccotti, which appeared a few months ago. And the plan for my talk is roughly like this. I'm going to talk about some general features of n equal to 2 supersymmetry theories in 4 dimensions. The definition of what we mean by a subset of these ones we call complete ones. And then classifying all the complete ones. And then interpretation of what physically this classification means, and then discuss some open questions. So I understand that half or more than half the audience is are mathematicians here, so I have to give some motivation for all this, perhaps. But perhaps the first motivation for n equal to 2 in 4 dimension is that we already know it's connected to interesting math from the work of Seiberg-Witten and the connection to Donaldson invariance and so forth. So we already know it's an interesting subclass of theories to focus on for the n equal to 2 theories. And if just one of them, SU2 theory, was so nice, what about all the rest? And how can we talk about all of them as motivation for understanding this notion of classification of these theories? That's perhaps a mathematical motivation of understanding what this class is. So these theories, 4-dimensional n equal to 2 theories, have interesting elements in the Hilbert space, which we call BPS states. And these states are captured by certain charges, electric and magnetic charges, and some flavored charges, additional charges that they may be associated with. And given a charge, an electric and a magnetic charge and a flavored charge, we define a vector in a 2R plus F dimensional space where R is the rank of the gauge group. So the Q has R elements for Q and R for P, so it gets 2R dimensional space for electric and magnetic charges. And the flavor is, I call it rank F. So you have a 2R plus F dimensional lattice that this belongs to. And in these theories, we have a map from this elements of this vector space to complex numbers. It's a linear map. And for BPS states, it has a property that the mass associated to the corresponding state is given by the absolute value of this complex number. Generally speaking, the mass, there's an inequality. The mass is bigger than or equal to this for general states with this particular charge. But for BPS states, this is saturated. And the question is, what good these BPS states are? What are these? What do we use them for? Well, they are somehow special because they saturate the bound, and in supersymmetric language, it means they preserve a certain amount of supersymmetry. And the question is, if I give you this spectrum, can it completely characterize the theory? In other words, it reverts the question of how you study the theory. Can I just study with the lattice, start with the lattice, and give you certain degeneracies? And can that be enough to define a theory? What BPS states are allowed? Presumably, I cannot give random association of certain number degeneracies for each vector element. There should be some consistency rules. What are the consistent theories correspond to as far as the choices of the degeneracies of these BPS states? And on the reverse side, if I am given a particular theory, like a gauge theory, SU2, SU3, or whatever gauge group is, can we figure out what these degeneracies are? So these are the set of physics questions that we will be interested in. From the viewpoint of characterization to physicists, this is especially the first question, can BPS states characterize the theory, is reversed from the usual way of asking the questions. Usually we start in the physics with the ultraviolet theory from short distances, and we figure out how things behave at long distances. This is asking the inverse question. It says, if I give you what theory looks like at long distances, can that be a good theory? That, of course, is desirable if we could manage to do that, because usually that's easier to describe the theory in the long distances. But the downside is that usually we don't know what are the consistency conditions for good assignments. And here our goal is to figure out what those assignments are. So it's a non-trivial task. If we come up with rules, this would completely change the way we think about the theory. Instead of giving a Lagrangian and short distance, we start the theory with a large distance. It is something in the gravity we would be interested in, describing the gravity, for example. That's like the infrared physics, and figuring out the analog of the quantum gravity would be the short distance version of it. So this is the reverse version of the question. So at the outset, you might be pessimistic about this program, because usually we start with the UV and we end up with IR, not the reverse. And here we're trying to change the order. So quivers have been, now suddenly I switch gears to quivers. What is quivers about? Well, quivers have been known to arise in both math and physics. In the physics context, in the context of D-branes, it was discovered by Douglas and Moore to be relevant in two particular possible ways in physics. One is to characterize a particular gauge theory. What gauge theory we have, what representations we have, what interactions we get. Or it could be interpreted by, in a different way, as giving rise to supersymmetric quantum mechanics, which characterize the dynamics of BPS states. So either as a higher dimensional quantum field theory, or as a one-dimensional quantum field theory, which is what we call the quantum mechanics, supersymmetric quantum mechanics. In two possible ways, we could be using this. Of course, this second one can be viewed as a special case of the first one, but I distinguish them because I specifically am interested in the second way of viewing the quiver. An example is, for instance, if you are talking about n equal to 2 gauge theories, if you're talking about SU2 gauge theory with no matter, the quiver for it is a little boring. It's just a circle with a 2 in there. That's just, you have a pure SU2 gauge theory. That's a theory in 4 dimension. And the corresponding BPS states, it turns out to be characterized by 2 nodes with 2 arrows going from one to the other. And we don't put a specific label on these 2 nodes, and we allow it to, in other words, we can fix it, but then you have to allow it to vary over all positive integers. And this corresponds to a UN times UM gauge theory, or if you wish, a representation of a quiver where the dimension here is n and dimension there is m. So the representation of this quiver captures the BPS states of this theory. So we have 2 different versions of this same theory. So this was the theory, for example, solved by Seiberg and Witten. And this will be the states which characterize the infrared properties of this theory. Now, how do we know this? Well, we know that in the case of the SU2, in certain region which is called the strong coupling region, we only have 2 stable particles which correspond to an electric state, a magnetic state, a monopole, which I denoted by 0 electric charge and -1 magnetic charge, and a dionic state, which I denote by 2, 1. These 2 characterize the stable BPS states in certain strong coupling region of this theory. And it turns out that these characterize one-to-one to the corresponding nodes of the BPS quiver. And the inner product between these 2 vectors, by the this lattice of electric and magnetic charge, is a coupled natural pairing, symplectic pairing, which is basically this times that minus this times that, which gives you, in this case, 2, which corresponds to the fact that I have 2 arrows here between one to the other. So the number of arrows is the inner product between the corresponding elements. So this defines for you a quiver, and simply the characterization of the representation of this theory gives you the states of this BPS, states of this SU2 theory. There is a stability condition which has to do with assignment of a complex number to these corresponding nodes, which is the same complex number associated with the BPS particles. Depending on the choices of that, the representation theory could give rise only to 2 stable objects, these 2, or to an infinite tower of them. And so there are 2 different regions in this theory, weak coupling and strong coupling, and both regions are captured by this same quiver. It's a very simple theory. So from this, the upshot is that for each node of this quiver corresponds to a vector, a particular vector in this 2r plus f dimensional lattice I talked about. And the number of nodes should be, in these theories, given by 2r plus f, because I want to be able to get all possible elements of the vector space. You have to have a basis for this vector space, so you have to have at least a number of nodes equal to 2r plus f. And if you assign degeneracies ni, or the rank of the representations to each node ni, the corresponding vector that you're talking about for BPS states will be the summation of these vectors with the corresponding degeneracies. And this corresponds to studying a supersymmetric quantum mechanics, which has gauge group product of the U and I. So it's rank Ni for each of these nodes. We also restrict the corresponding complex numbers to be in the upper half plane. So we have a bunch of these nodes, and these complex numbers represent the corresponding central charges, and the corresponding anti-BPS states will be corresponding to the -1. So each complex phase comes with a -1 corresponding to the corresponding antiparticle. So the first question is, do all n equal to 2 theories in 4 dimension admit BPS quivers? Can we find BPS quivers for any given n equal to 2 theory? And the answer turns out to be no, with a very simple counterexample. The counterexample being n equals to 4 supersymmetric Yang-Mills viewed as an n equal to 2. If you turn off the mass of the adjoint for the n equal to 2 adjoint field, this corresponds to an n equals to 4 supersymmetric Yang-Mills. We do know that BPS degeneracies for this theory. It is given by electric and magnetic charges with arbitrary relatively prime numbers, p and q, which means that if you look at the corresponding vectors that you get on the 2 dimensions, you get a dense set of phases around the circle as you go in the phase of these complex numbers for the BPS states, which in particular means you cannot have a generator for the corresponding quiver in the upper half plane, because you will not have a complex, a dense phase everywhere for these. Therefore, this we know cannot be given by a quiver theory, except it turns out that if you do turn on the mass, even for this theory, if you turn it on, there is a quiver capturing this. So this n equals to theory, this famous theory, once you give a mass to the adjoint, does admit a quiver, it turns out. However, there are other n equal to 2 theories which do not admit similar mass terms. They don't have those mass terms allowed in their theory, and I will mention examples of it later. These theories will not have necessarily quivers. So these are more subtle, and these typically arise when you have a dense set of BPS states. So when you have a situation where the BPS states cannot be have an everywhere dense spectrum in their phase, in their BPS complex number, then it's going to be tough to get quivers, and these do happen sometimes. These other ones are simpler, and they have kind of a more milder behavior. Both of them are physically fine. It's just one of them is harder to understand. Now, as we change the choice of the basis, we will have to change the quiver. So once we have a particular choice of the upper half planes, we have resigned ourselves to a particular set of BPS states. But occasionally, some of these complex numbers might leave the upper half plane, or we might choose how we cut the alternatively, we could choose how we cut the upper half plane, in which case one of them leaves the plane and the other one enters. And therefore, we have to do something. We have to change the BPS states to the anti-BPS states. We have to do some transformation on the quiver. And this is called the quiver mutation. This is actually well studied by mathematicians. And the idea is that therefore, if you start with the given theory, once you change these complex parameters as you change the theory itself, the universality class of the theory doesn't change, but the quiver that it represents changes. So we have to study representation. We have to study quivers up to these transformations, known as mutations. So if you have a particular one of these BPS states, which I've denoted here by this node, green node, which is attached to some other nodes by some arrows, if I do mutation, if this one leaves the upper half plane, what happens? You do mutation on the quiver, which means, first of all, you change the direction of the incoming and outgoing arrows to the opposite. You reverse their directions. And in addition, you introduce also new arrows between quivers that between corresponding states that you used to have. Namely, for each pair that you had before, you introduce a new field here, which in physics terminology, what we would have called is meson fields. So the original meson fields would be these blue lines that we have to introduce, and you also get a certain superpotential term. This is familiar to physicists from the viewpoint of what we call Seiberg dualities. So Seiberg dualities is exactly this kind of operation. You get these meson fields on the dual theory with these arrows changing direction with an additional superpotential term. The only difference is that this does not have to. This is not a 4D n equals to 1 theory. In fact, It's not even, if you view it as a 4D theory, it would be even anomalous. The number of arrows incoming and outgoing may not be the same. So this operation is like cyber dualities, but it's just an operation on the quiver. And it turns out that the representation of the quiver doesn't change drastically. It's an equivalent representation of the quiver. And this is the way we think about it physically, as a cyber-like dualities. So just to get started, we'll give a simple example. Suppose you have a quiver like this, with arrows like this, and suppose you try to mutate this particular node. This just corresponds to changing the direction of that arrow, that's all. Now suppose you try to mutate this guy. If you try to mutate this guy, you change the direction of these two arrows, but you also have this meson field, so you have to introduce a new line here. So you get this kind of a quiver with a superpotential term which corresponds to going around the loop here. Now, how do we determine the BPS quivers associated to a given gauge theory? I already told you what it is for the corresponding SU2 theory. For the SU2 theory, you just have an affine A1 quiver, and that's the end of that story, and the representation of that has been studied by mathematicians, going all the way back to the works of Katz 30 years ago. So this is long before Seiberg and Witten studied their spectrum. Representation theory of these guys were studied by mathematicians. We physicists are behind in this game, I guess. But we're trying to catch up, and we're trying to get other kind of gauge groups for this. So we start with an SU2 gauge theory with certain other matter fields. We want to see how you go from this quiver to the other one. So for example, suppose we are studying SU2 gauge theory with one flavor. The claim is that the corresponding quiver is this one. Now, how do we come up with that? Well, if you take the mass of this flavor to be infinite, then you have a decoupled SU2 theory. So it's natural to have an SU2 subquiver in the story. But then if you think mass is not infinite but finite but large, you should get at least one extra electric state, which corresponds to this mass state. So you have to have one more element in your quiver, which is that element that was missing, which is this corresponding massive flavor. And you have to choose whether you choose it with a plus or minus 1 as far as the fundamental. You choose it to be the top component of the fundamental or the bottom component. And you have to choose the bottom component because you have to take by linear combination of these vectors with positive coefficients, the plus 1, 0. And since if you add these two guys together, you get 2, 0, you see that you have to choose the minus 1 there. And once you choose that minus 1, 0, the inner product of minus 1, 0 with these other two vectors determines the direction of the arrows and the degeneracies. So you get the unique quiver. So the quiver is completely characterized by this condition that SU2 with NF equals to 1. So once you know this SU2 theory, you're coming up with what the quiver is for a completely new theory, SU2 with one flavor. And representation theory of this is going to give you all the states of SU2 with one flavor. That sounds amazingly simple, almost trivial. It had no right to be this simple. The SU2 with one flavor is a completely new theory. We cannot expect it to be this simple. And the claim is it's that simple. Well, what about if you have more than one flavor? Well, you do the same game. You take these masses larger and larger. And so one by one, you can add them up. You can add them back in. Each flavor will give you an extra state, extra node in the quiver, and the corresponding diagram you can complete yourselves. So the theory just simply becomes for SU2 with NF flavors, will become a diagram with two arrows and these corresponding triangular kind of configurations for each flavor node that you have added. OK. That sounded simple. Now I come to the definition of what we mean by complete n equal to 2 theories. The question is, I talked about these central charges, these complex numbers z, which you associate to each vector. And the question is, can you vary them arbitrarily? In other words, when we talked about, for example, representation of the quiver, there's a stability condition characterized by a complex number associated to each node. Could you physically change these complex numbers arbitrarily? Of course, mathematically, you say, I can choose anything I want. You just choose complex numbers, whatever you want. But the question is, does that arise in physics arbitrarily? And it turns out the answer to that is no. In physics context, you don't get necessarily maximally free choices of these complex numbers for generic theories. So in fact, if you had, the dimension of the moduli space would be 2R plus F. Namely, for each node, you have a choice of a complex number, so you have a 2R plus F dimensional complex moduli. Now, of course, naively, you would think that if you specify the electric charges, the magnetic ones are fixed by special geometry, the A periods determining the dual periods. That will be true if the theory is compact, but if it's not compact, you have extra parameters like masses, coupling constants, and all that, which could vary. And so this could be bigger than R, but the question is, could it be as big as 2R plus F? And it turns out, at least for SU2 gauge theories with hypermultiplets, this will be 2R plus F dimensional. So suppose you have gauge group being R factors, the product of SU2 with R factors, R such SU2s. For each one of these SU2s, you get one electric charge. So you have R electric charge and R magnetic charge. So this is the case that you get. The rank is 2R plus F, and F is the number of flavors which you can put between them by fundamentals or whatever you may want to add. And in this case, you do have the dimension of the modular space being 2R plus F. Namely, for each SU2, you have the Coulomb parameter. But also for each SU2, you have its coupling constant. So you have two R parameters, one coming from Coulomb parameter and one from its coupling constant. And then you have these mass parameters for bifundamentals for each flavor. So you indeed get 2R plus F dimensional flavor, F dimensional moduli space. So for SU2 gauge theories, we have an example that you can get arbitrary complex numbers. Now, this is not necessarily the case for higher gauge groups. For example, if you study SUN gauge groups, just let's say pure SUN gauge theory, you have n minus 1 dimensional Coulomb branch, but you only have one coupling constant. So instead of getting 2 times n minus 1, you get n minus 1 just plus 1. So you won't get the moduli space being complete in that sense. So therefore, SUN gauge theories are incomplete in this sense. So here we see that the minimal rank one, the SU2 ones, are singled out as being the interesting ones in this sense. Of course, there's nothing physically wrong with higher rank gauge groups. You can study them. But it just means that the dimension of the corresponding modular space is less than the number of nodes. In other words, you will have to solve a Schottky-like problem for this theory. You will have to say which subspace of the complex phase, complex BPS states are occupied. Whereas these complete theories don't have the analog of Schottky problem. It's trivial. Everyone is allowed. So in some sense, it's simpler to study these complete theories. So the question is, OK, we now have a definition of what these complete theories are. Can we actually completely characterize what they are? Can we actually classify what they are? And in particular, are the BPS quivers for complete theories special in any way? Now, it turns out that there's already a hint. If the complex numbers Z, the BPS complex numbers, can be arbitrarily varied, then you can move them anywhere you want, and therefore arbitrary mutations can be induced because you will have to allow for every complex vector you wish, every node to leave the upper half plane, and you have to do the mutation on the theory. So if you are talking about complete gauge theories, therefore arbitrary mutations in any order you wish should be allowed. Therefore, the question is, do arbitrary mutations look OK in these theories? Well, let's study what happens when you take mutations. Suppose you take this quiver with 3 nodes and 3 arrows between each pair of nodes in the way I've indicated. And suppose you do mutation, let's say, on this node. And this corresponds to reversing the direction of these 2 arrows and changing this degeneracy by 3 times 3, which is 9, going the other way. So the net number being 6 going this way. You can then do mutation on this node, let's say next, and then you change the direction of the arrows here, and then you change the number here to 15. And so you can see that the number of quivers, the degeneracy is going to be becoming explosive as you do this. If you do the corresponding order of these mutations in a suitable way, you can get these numbers arbitrarily large. But that's beginning to look bizarre because you're having a bizarre system which could be arbitrarily arbitrary number of bifundamentals between these pairs describing the theory without any bound. That sounds bizarre. So since arbitrary mutations are allowed, but arbitrary mutations could do nasty stuff like take these numbers out of range, you could be motivated to restrict it. So for generic BPS cover, we should expect only finitely many mutations. Otherwise, we'll get this bizarre growing numbers, which looks very unphysical. But since for our complete theories, arbitrary mutations are allowed, this strongly suggests this conjecture that complete n equal to 2 theories, which have BPS covers, should only have a finite orbit under mutations. That if you do mutations, you cannot get infinitely many diversity. You should come back to itself after a finite number of steps. There's another argument to motivate this conjecture, which I will talk later. But before doing that, let's just see motivation for this conjecture through an example, which is the same SU2 example I started with, and that is with which we studied with the number of flavors. We know that if you have SU2 gauge theory, if the number of flavors is more than 4, the theory is bad. This is the first test. You see, if you take SU2 gauge theories, and if I tell you have a bunch of flavors, and in the infrared the theory looks this way or that way, it would be hard to predict that the theory is good or not in the ultraviolet. For example, from the ultraviolet study of the theory, we do know that the theory will not be asymptotically free if the NF is bigger than 4. That means the theory is incomplete in the usual sense of UV incompletion. The question is, does the quiver know about this? Does the BPS quiver I told you about, that boring 2-node thing where you added these extra triangles, know about it? Well, let's see. Let's take this SU2 theory we started with, and we said the mutation corresponding to the reversing of this arrow. So the mutation on the corresponding SU2 quiver is a bit boring. If you have one flavor, reversing of if you just put an extra mutation, the only interesting one you can do is here, but that just gives you this one, which is okay. It's some kind of a quiver. It doesn't look bizarre or anything. Looks fine. But now let's look at NF equals to 4. If you have an F equals to 4, as I mentioned, for each fundamental flavor, we are putting one extra node, so you have 4 of these extra nodes. And you could start doing mutations on these guys. So suppose you do a mutation there. So you're going to reverse the direction of these 2 arrows and change the net number of here by 1 arrow going this way, which means this 2 goes down by 1. So it should go like to this. Next, we can do the mutation on the second node. Again, the direction of these 2 arrows should change, and the net number here is going to be 1 going in the opposite direction, meson. Therefore, this net number is going to be 0, so that link is going to disappear. And so we can repeat this for the next node and then do the mutation there, and we get now 1 node in the other direction. And if you do the last mutation, you're back to the original SU2 quiver with the F equals to 4. And if you had more than this, if you had one more, you could have made this 3 lines. And it turns out as soon as you do 3 lines, you can continue this and get arbitrarily large number. But the highest number you can have is 4 if you don't want this number to grow out of hand. So the number being 4 from this quiver is completely characterized by the mutation being finite type. Remarkable. The infrared physics seems to know about the UV physics of the theory being incomplete. This is amazing. That we rarely see this in this simple form. As an imprint of the UV completion in the infrared physics, we can say that there cannot be any more than 4 flavors. So not only the theory is mutation finite, even though I haven't proven it, I've just tried to give you an indication, this property knows about asymptotic freedom. And the fact that the 4 is the limit where this can happen, and that's the point which actually corresponds to the beta function vanishing, which is the conformal limit. So as I just said already, just to repeat, the completeness means the central charges can vary arbitrarily. The rank of the lattice is the number of nodes, and the dimension of the moduli space is the number of nodes. So that's the set of the theories we're talking about. That complete n equal to 2 theory should have finite mutation type follows from another conjecture in another paper, which we had with Sergio and with Andy Knightsky, which is what we call the 4D 2D correspondence principle. To every UV complete n equal to 2 theory in 4 dimensions corresponds to an n equal to 2 theory in 2 dimensions, which corresponds to what the worksheet of that theory sees. So if you have a UV theory, if you imagine that this theory is engineered in type 2B strings, let's say, then you have a worksheet theory which has n equal to 2 supersymmetry, And you can ask what kind of n equal 2 supersymmetric theories you can see on the worksheet. And it turns out that using this kind of map and disentangling the Liouville degree of freedom, you can map the data of the 4D quiver to the data of the 2D corresponding n equal to 2 2D theory, where the BPS quivers get mapped to the soliton data in 2 dimension. The nodes of the quiver get mapped to 2D vacua, and the links get mapped to the solitons. So this is an interesting map where you actually think about each node we had as a vacuum, and each thing connecting them as a kink, going from one side of the universe to the other in 1+1 dimension. And it turns out that in this language, complete theories, to have a theory which is complete, translates to the condition that you can deform all the chiral fields in the n equal to 2 language, which means the central charge is less than or equal to 1. That's a well-known condition because the maximal central charge is the central charge of the theory, and all of them should be less than or equal to 1 if you want to vary them arbitrarily. And through the work we did with Ceccati in the 90s, it put some restrictions from the TT star geometry. And in particular, for example, it implies that the number of links between any two nodes should be less than or equal to 2 for it to be mutation finite. So already we are now going back to some of the work we did, which actually can now feed from 2D back to 4D, telling us some properties of 4D physics from certain data in 2D. So just to give an example, if you are interested in general theories, for example, you can ask, what does the 4D 2D correspondence predict for the SU N-Yang-Mills BPS quiver? And the answer turns out to be this quiver. So you can actually, I already told you for SU2 what the theory is, which was just 2 nodes. This is the, if you're interested in representation theory, the BPS quivers for SUN theory, this will be the quiver. If you want to add fundamental fields, you do exactly the same game as I did with the adding masses, and you can have extra nodes which couple to this theory. So you can actually construct all these quivers for arbitrary gauge groups and arbitrary matter. It's a very powerful principle. So now in principle, just studying the representation of the quiver, we can answer all the possible BPS states you can have for any gauge group with any representation with n equal to 2 in 4 dimension. That's remarkably powerful without actually doing much more in some sense. Now, so motivated by mutation finiteness criteria, we can ask, can we classify them? And luckily for us, this has been done by our mathematician friends, Felixson, Shapiro, and Tumarkin. There are 3 types they find. If it's 2 nodes, there's no restriction. You can have arbitrary 2 nodes with arbitrary number of links between them. You can have quivers associated with ideal triangulation of bordered Riemann surfaces. These are the kind of quivers which were studied by Fomin, Shapiro, and Thurston. And then in addition, there are 11 exceptional cases. So this is the full list of BPS quivers which are finite mutation type come back to itself, which don't have any self loops. So I forgot to say, I'm assuming that there are no self loops because you could add a typical superpotential to them to get rid of them. So I'm assuming that's not going to be relevant for classification of the complete theories. So if you restrict, not have those, this is the full list. And these cases, cases 2 and 3 correspond to physical theories. The case 1, the ones which have less than 3 lines, 3 arrows, are good in the physical sense. But the other ones aren't. It's already remarkable that essentially all the complete quiver theories are good physical theories. This was a necessary condition for the theory to be good, not sufficient. Here I'm saying it's almost sufficient too, except for this case. And in some sense, we could have excluded this theory because we know that the 2 and the 3 only give you at most 2 links between any 2 nodes. That's part of the classification that they find. You cannot have more than 2 links. Otherwise, you can do mutations to get the numbers arbitrarily large. And therefore, you could have excluded this by just that criteria that the number of links being less than or equal to 2. So the case 1 would be 2 nodes with 1 or 2 links between them, but not more than 2. And this case is a subcase of case 2 that we just discussed. So this case with less than 2 or less links is a special case of this one, so we might as well forget about it. We're just talking only about cases 2 and 3. And the cases 2 and 3 were studied, well, the corresponding quiver for them were studied by mathematicians, what they call the ideal triangulations of these bordered Riemann surfaces. Here I'm just giving some examples. You have basically a Riemann surface with a certain number of punctures or borders. Borders can also be viewed as punctures with higher order poles or irregular singularities in the Hitchens system. And for example, this theory corresponds to SU2 so if you look at the ideal triangulation, you have for each edge of the ideal triangulation, you get a node. And for each triangle for them, you get a link. So that's how you associate with the ideal triangulation a corresponding quiver. Here you see you have three edges for this ideal triangulation. So these are the 3 nodes. And you can find 3 triangles that they border, and therefore you get 2 to 2s. 2 is between each pairs. So that's why you get this structure. And then there's an orientation having to do with, once you orient these links, you can find the direction to this arrow. So they find a map between the corresponding ideal triangulation and corresponding quivers, and they find that these are precisely mutation finite. And they find nice building blocks. Basically, they show that everything can be built up from these quivers, where you just glue these blue nodes to each other, and these are the puzzle pieces for them. From these, you can get arbitrary quivers that are relevant for this. So what is the physics of this? Well, it turns out that these can be identified with the theories that Gaiotto, Moore, and Knightsky studies. They correspond to 2 5-range wrapping Riemann surfaces with punctures, with certain singularity structures at the punctures. And the circular compactification of them leads to the corresponding Hitchens systems. So these triangulations correspond to the quivers that you get corresponds to these physical theories. We can identify them, again, using the 4D, 2D correspondence. And so I won't get to the detail of that, but let me move on to the exceptional cases. There are 11 exceptional cases, and these 11 exceptional cases corresponds to the E-series type of quivers, E6, E7, E8, affine E6, E7, E8, and elliptic E6, E7, E8. These are 9 of them. And then there are 2 leftover cases, X6 and X7, that we'll mention what they mean. So the E cases, the E quivers we already know. These are just the regular E Dynkin diagrams. The affine E also the affine Dynkin diagrams. And then these elliptic E's can be viewed in this way. You take a quiver which has 2 lines, like the SU2, and then you attach to it these extra three legs like this, attached to each one of those 2 nodes, where the number of nodes that you can add are restricted. So the N1, N2, and N3 are being 2. You get the elliptic E6. 1, 3, 3, you get elliptic E7. And 1, 2, 5, you get elliptic E8. These are the corresponding quivers. And finally, the X6 and X7 are these 2 cases. So you get X7 has 7 nodes with these degeneracies 2s and these outer links, and 1 everywhere else. X6 looks like a subquiver here, where you just get rid of this one of these nodes, basically. So X6 is kind of, it can be viewed as a deformation of X7, but this X7 is kind of left over there. Now we interpret these exceptional cases. The exceptional cases turn out, by this 4D, 2D correspondence, to map to these local Calabi-Yau singularities. You simply have elliptic type singularities in this form. The double E6 corresponds to x cubed, y cubed plus u cubed. So there's 3, 3, 3, 4, 4, 2, and 3, 6, 2 are the familiar 3 elliptic forms that you can have. But now we view them as a local singularity of a Calabi-Yau threefold with an extra boring quadratic piece. And then affine E's can be viewed just like these with some of these powers lowered. So the affine E's and the lower ones can be viewed as sub-pieces or deformations of this structure. This is the highest one among them. As you can see, these don't correspond anymore to Seiberg-Witten type curves because they don't involve just 2 variables. Well, at least some of them don't. These do, but these don't. So this cannot be viewed in the usual Riemann surface form, for example, but certainly fine from the viewpoint of a Calabi-Yau singularity, which means it's fine in string theory because type 2b in these geometries, you can get these. We can also describe gauge theories, which in low energy limit give rise to the same corresponding n equal to 2 geometry, but let me not describe that. So these are the E6, E7, E8 cases, which can also be viewed as special cases of the other ones. And so I won't spend too much time on it. And finally, the X6 and X7. Well, X6 and X7, we kind of know how it works, because we already said that the two line ones is SU2. And if we have a node, this subquiver here corresponds to SU2 with the fundamental. But this node is a fundamental not only just to that, but also to this guy and to this guy, which means that it is triply fundamental, trifundamental, for 3 SU2s. So this corresponds to SU2 cube gauge theory with the matter field 222. So we identified all of these gauge theories with some particular form. It's amazing that we identify all of the ones we know are identified with something and nothing more. Well, except we have to be a bit more clear. When we said that these quivers correspond to bored Riemann surfaces with punctures, they do have to have at least one puncture. And if you don't have any punctures, you cannot write the corresponding quiver for it. Whereas the gauge theory, 4D gauge theories with n equal to 2 without punctures seem perfectly fine. For example, if you take a genus 2 Riemann surface and wrap 2 5 branes around it with no punctures, that theory is fine. And indeed, it corresponds to SU2 cubed gauge theory with 2 half hypermultiplets in representation 222, 222. So together, they form SU2 cubed with the 222 I was talking about. So why was not this on the list before? Well, the reason it was not on the list is that to get it on the list, you have to give mass to these guys. And the corresponding 5-brane description precludes that, because these are different points. But from gauge theory viewpoint, there's nothing wrong with giving mass to this bifundamental. And so precisely for the genus 2 GMN theory with rank 2 curve, you can actually give mass to the theory. And that gives you the corresponding quiver X7. So that's why genus 2 is special. So the corresponding genus 2 Hitchin system with no punctures is singled out among all the Riemann surfaces with no punctures as the one which can admit a quiver when you give a mass deformation. But the higher one, the higher genus ones, won't work like that. For example, if you have genus 3, for each of these nodes, you get trifundamental, but trifundamentals of different gauge groups. Therefore, you cannot give masses to them. You cannot pair them up anymore. And therefore, this theory cannot admit masses, and therefore, they will not have mass deformations, and the BPS states will form a dense set on the circle of the complex plane in their BPS space. So that's why we don't see those, but we did see the other one as a special case. OK, so I already talked about this. And then we can give other gauge theory interpretation for various other ones. I think I'm beginning to run out of time, so let me just try to get some extra simple statements here. The theory with a Riemann surface of Hitchin type with this regular puncture and an irregular puncture of higher order corresponds to a quiver of the N type. And it turns out that you can gauge this one. You can connect this to an SU2. And if you gauge it, it corresponds this to a matter SU2, an SU2 matter with the corresponding effective number of flavors to be slightly less than 2, namely 2 minus 2 over n. So you can put an irregular singularity and glue it to the rest of the Riemann surface with an SU2 gauging. Since this will give you, this piece of the Riemann surface will give you 2 fundamentals. And this one will give you 2 minus 2 over n. Together, they are less than 4. It's fine. So you can have an asymptotically-free theory. And you can have a gauge theory interpretation of what this operation means. Let me not. So in other words, the corresponding exceptional theories can be viewed as SU2 theories coupled to 3 DN theories gauged. So in other words, these DN gauge theories, the Argyris-Douglas DN theories, have an SU2 gauge symmetry, which can be gauged. And these are tri-fundamental, tri-matter representations of these DN. So you can have a purely gauge theoretic interpretation of these theories as SU2 theory coupled with some exotic matter systems. OK, I think I'm running out of time. So I'll go to my conclusions. So these ideas show the importance of BPS states in understanding N-equal 2 theories. And we have seen that in many cases, in cases where their quiver states, their BPS states are not dense, they are captured by quivers. And at least all the ones we know are in the list. And we have described all of them in a very simple, effective way. So this is a very powerful way to think about these N-equal 2 theories. Now, we have also seen that there are some non-quiver n equals 2 theories, like the one corresponding to higher genus cases with genus began 2 without punctures. We know they exist. We know they're good gauge theories. And we do know there's no quiver associated with them because they have everywhere dense phase in the BPS state. So are there other ones other than these, or that's it? That's an open question. We do not know the answer to that. Now, it also seems that not all the quiver mutations are physically sensible. How to characterize good ones? Well, in the case of the complete ones, all the mutations were good. But for the other ones, all of them shouldn't be good because you get all these crazy large numbers. So therefore, not all the mutations should be possible. Of course, this is consistent with the fact that the central charges has a Schottky problem, so you cannot do anything you want. So the problem is more restricted. And the question is, can we have an algebraic characterization of what is allowed as far as these mutations are concerned? If we had this, and if we had this understood which finite set of mutations are possible, which we conjecture, it's always true that for any gauge theory, you should have only finite number of mutations, but only very special ones are allowed, then we would be on our way to classify all n equal to 2 theories which admit BPS quivers, and this would be a very powerful way of characterizing all theories with 4D with n equal to 2. So this is an important open question that we need to figure out if we want to use these BPS quivers to classify all n equal to 2 theories in 4-dimensional. Thank you.
Any questions?
So are those quiver gauge theory has a topology person, so we can use to define smooth invariant.
Presumably, yes. Yes. I mean, the answer is you can. Whether they are interesting or not is a different question, but yes. So all the 4D theories, all the 4D n equal to 2 theories can be twisted, and therefore you can do corresponding thing that's written in it.
That genus tutor with no punctures. So you say it has a gas deformation that's sort of not visible in the diagram. So that would correspond to some deformation of the Hitchin space.
Not necessarily Hitchin space. I would think that the corresponding system is not given by curvature. Therefore, there should be another, in that framework, there is no deformation. Therefore, you are not, if you restrict to the Hitchin subspace, you cannot give mass, period. So the question would be, what's the corresponding analog of Cyber-Witten curve, for example? Which we don't know. In other words, the answer is not known if you turn on the mass. How you characterize the corresponding Cyber-Witten geometry and all that.
But the coaxial threefold will be there.
No, the analog of the spectral curve of the Hitchin system, in that case, is not known because by definition it's not part of the system. But we do know there must be an extension of the Hitchin system for which there would be spectral curve, would be the corresponding Cyber-Witten curve. Yes.
But will there be a coaxial threefold?
Yes. It better be. It better be that there's a Calabi threefold. It better be that there's a Calabi threefold whose corresponding spectral curve describes the corresponding Calabi threefold. Yes.
Other questions?
Do these triangulations of Riemann surfaces give insights into which duality is allowed, which cyber-duality is allowed?
Well, this triangulation gives you an explanation of which quivers arise in the corresponding examples we described. Well, so for the rank 2 case, all the cyber-dualities are allowed. For the higher rank case, it's not known how to use the analog of these ideal triangulations for this course. So the answer to that is not known. So that's a good question. The analog of this ideal triangulation of higher rank case is not done.
If you go to some nearly complete theory, where you're off this by small number, can you describe, is it clear what the image will be, what the equations are?
Well, for some examples, for example, if you take the SUN, pure SUN Yang-Mills, we know the Cyber-Witten geometry. Therefore, we know the answer for what they are. We know what kind of periods arise because we know how to compute the theory's integral. We know how the periods work. So we know the answer. In some special cases, what is that? The analog of the Schottky problem is solved by the Cyber-Witten geometry. But the question is, how do you characterize it in conjunction with the corresponding quiver? And what kind of mutation does that mean for the quiver? And that has not been studied, though it should be possible to study. We do have the technology. It's just a matter of studying it.